Right, so now we'll make a start. And remember, last time what we did was we talked about revision about things for ordinary differential equations. And then we talked about the idea of a Fourier series, saying that a claim that you could write any function, periodic function, as a function of sines and cosines. And then we ended up talking about periodic functions and odd and even functions. So we finished the lecture last time, remember, with this definition for a periodic function, where if f of x is defined for all x, and you can find a p bigger than 0, so that this holds for all x, then f is periodic with period p. So what we're going to do today is do a bit more work on the definitions of periodic functions and examples, talk about odd and even functions, and then go to Fourier series and discuss how you actually calculate the Fourier series. Okay? So we're going to start off by some sort of exercises here. So f of x equals c constant. Well, that's periodic. But does not have a prime period. Remember, the prime period was if there exists a smallest such p, so that this holds. And here you see it'll hold for any p. Okay? Example 2, f of x equals sine x. Well, that's periodic. And because f of x plus 2n pi will give you f of x. And so the prime period is 2 pi. F of x equals cos 2 pi x over a. That's periodic. It's cos, so it's periodic. And that's got the prime period a. Because if you think about it, if you increase x by make it x plus a, then you've essentially added another 2 pi. And then if we have cos 2 pi n x over a for n integer bigger than 1, then the prime period is a over n. Okay, and just quickly, how do we do that? Cos 2 pi x, x plus p over a equals cos 2n pi x over a, which is the f of x, plus 2n pi p over a. And then we want this to be 2 pi. That's the minimum one. And so obviously p must be a over n. In another example, f of x equals x to the n. Well, that's not periodic. Okay? So all along we've been talking here about functions that have been defined for all x element of the real line. Okay? So now what we're going to do is we're going to talk, well, what happens if f is only defined on a subset of the real line? So suppose f of x is only defined on x element of alpha plus p. Oops, so that is closed, okay? Then we can perform a periodic extension of f. Okay, so it's very important. And what does that mean? So suppose here is alpha, and here's alpha plus p. And this is f. So f, and I assume you've come across this sort of notation before, it's not defined on alpha, so we put an open circle, and it's got some value at alpha plus p. So we put that as a filled circle, and suppose it looks something like that. Okay? So all the periodic extension does is simply take that and just put it like this. That direction and this direction. Okay? So what we will do, use a different color. This is alpha plus 2p. We simply shift this over to there. So that'll go here to here. Like that. And so what that means is, of course, still alpha, or f at alpha plus p will be this value. Then next one be here, go on like that to there. And then going down here, alpha minus p, we just shift it over to there. So that one will be here, and that one will be here. And then we'll have like this. And so now we actually define f at alpha to be this. Okay? So what we will do with the Fourier series when we get on to it, we'll start off with the Fourier series, which is for f that's defined on a segment of the line that's length 2 pi. Or in fact, we could do it in general. We could say, let's have a function defined on all x that's got period 2 pi. Then we can write a Fourier series for that. And that's what we will do. So then a natural question for you to ask would be, well, what happens if my function is not defined on all of the real line? What happens if it's not periodic? Or what happens if it's not got period 2 pi? Right? Well, if it's not periodic, this will make it periodic. And if it's not got period 2 pi, well, we show how we can redefine to make it period 2 pi. Okay? So that's why this sort of idea is very, very important. And another thing you should notice here is that it's discontinuous here. So there would be questions there. What does it mean to say you converge to this function if it's discontinuous? Because if you have an infinite series that converges to this point. And if you make it converges here, if you make x, it converges here. If you make x here, it converges to here. X here, it converges to here. X here, it converges to here. So this infinite sum from here is converging to here. And from here is converging to there. What happens at this point here? So we'll take that into account as well. Okay? So let's do this now more formally rather than just as by drawing a diagram. So this definition. And as usual in this course, remember I said last time, I'm not going to copy out all the notes. I'm just going to give examples of definitions. So make sure that you go back and read the full definitions in the notes and use those. I'm just going to highlight what are the key things. So basically, given any x, an element of the real line, there exists, so we're thinking of this function here still, so there exists a unique integer m, which will depend on x, so you write it like that, such that x minus m of x, p, is an element of alpha plus p. So what does that mean? So suppose I start off with x here, then I would take m to be 0. So if I take m to be 0 in this definition, then my x lies between alpha and alpha plus p. Suppose my x was here, then if I take m to be 1, then x minus p lies here. Suppose my x was away over here, then I would go minus 1p, minus 2p, minus 3, 4, 5. Eventually I would get in there. Okay? And then if I was here, obviously I take negatives, get into there. M being negative. So then the definition the periodic extension big F of little f is f of x equals f of x minus m of x p. So in other words, if you want to find what should the value of the big F be at this point, I just go back minus p minus 2p minus 3p, take that value, and that's the value. And so in that way, I've defined this function now on the whole real line. And f is periodic with period p. F is periodic with period p. Now, what I mean by that, of course, prime period p, and then usually we end up just ignoring the prime and just doing period p. Okay? And that's sort of obvious from looking at here. This is repeating itself every p. Translation. But let's just prove it. If we take an x, so now what do we need to prove? So required to prove that f of x plus p equals f of x for all x. Okay? So definition, what is f of x plus p? Well, f of x, let's take f of x plus p. That must equal, by definition, little f of x minus some m. And what we can write that as x plus p, and the m, let's just write it as an m plus 1. Okay, because m's an integer, m plus 1 is an integer, so it doesn't really matter. So in other words, what we can say here is that since there will exist m of x such that m such that x plus p minus m plus 1, p is an element of alpha plus p, right? Because all we're saying is that if I take, that's again saying you x plus p, call that some other x hat or something. It's saying if I take an x hat, then if I go back a certain number of p steps, size p, I will get to here. That's all that is saying. This is equal to f at x so I've done this. Yeah, that's going to equal to f at x plus p minus that. And what is that equal to? That's equal to f of x minus mp. And what is that equal to? Well, by definition, that's equal to f of x, by definition. Okay? Because if I need to do m plus 1 steps to go from x plus p to get into here, then if I'm at x, I will need to do m steps to get back into here. Okay? So the key thing here is writing this like this, m plus 1, and then the p and p here cancel, and you get x minus mp, and that gives you that. Okay? Right, so now we'll go and look at properties of periodic functions. So, if f and g are periodic functions, with period p, then 1, f and g are periodic with period np for any p, for any n element of natural, ignoring 0. Okay, I leave that as an exercise. The way you do that is proved by induction. So I leave you to fill in the details here. But what you would do is you would say f of x plus np we write as f of x plus n minus 1p plus p. So what we've done there is written this as n minus 1 plus 1. By induction, that becomes x plus n minus 1p because we're assuming that it holds for n minus 1p, and then that's f of x. Okay, so leave you to fill in the details. For any alpha beta real, the linear combination alpha f plus beta g is periodic, period p. Leave you to prove that. Fg is periodic with period p. Leave you to prove that. For any lambda greater than 0, f of lambda x is periodic with period p over lambda. Leave you to prove that. I mean, that's sort of obvious. We'll want f of lambda times x plus the new period, call it p hat. So what we're really doing is it's really f of lambda x plus lambda p hat. That's got to equal f of lambda x plus p. So lambda p hat must be p. So p hat must be p over lambda. Okay. So for any, and now what we're going to do now, this is going to come in very useful when we're doing the Fourier series. So for any alpha real, the integral from 0 to p f of x dx is equal to the integral from alpha to alpha plus p f of x dx. Now intuitively that should be obvious, because if f of x is periodic with period p, then if you integrate it over a segment that's of length p, it shouldn't matter where you start. Okay? Because if I integrate this over here, that should be the same as if I integrated over here. Likewise, if I integrate it over here, it should be the same as integrating it over here. Okay? And the proof of that if we look at the integral alpha plus p f of x dx, well, that integral I can write as alpha to p f of x plus p to p plus alpha f of x dx. Or sorry, I've got that wrong way around. Sorry, it's a different proof. Okay? So, sorry, that was being a bit silly here. That's P alpha plus P, right? So we've just split alpha to alpha plus P up to alpha to P, P to X plus, to alpha plus P. Leave that as it is. And now this one here, let's put X hat to be X minus P. So X hat will go from 0 to alpha. Dx hat will be dx. And what about f? F of x is also f of x hat. Sorry, put in here x hat. That's that. Simply because f of x hat, well, by definition of x hat, that's that. But f is periodic with period p, so that's that. Okay, so f of x is that. Now look at this integral. This is just a dummy variable, so it doesn't matter what it's called. 0 to alpha plus alpha to p, integral 0 to p. So that's that. Okay. So now we're going to go and talk about odd and even functions. So definition, a function g going from R to R is said to be even if g of x equals g of minus x for all x an element of R. So in other words, when you change the value of x to minus x, you don't change the function. So x squared, for example, would be even. X to the fourth would be even. And as we did last time, cos x is an example of something that's even. Because it goes like this. Actually, that's very badly drawn. It's supposed to be something like that and like that. And so if I start off here and I take minus x, I go to here, I get the same value. So reflection in the y-axis gives you the same answer. And odd, so a function f going from R to R is said to be odd if f of x is minus f of minus x. So for example, x cubed, that function would be odd. And we did last time sine x. Remember, sine x looks like that and goes on. And so you see here, if I go to minus x, it's negative. So these are in the notes. So I'm going to leave you to look at the notes, but also give them as exercises. So to do this, if f and f1 are odd, g and g1 are even, then 1. If f is continuous, then f of naught equals naught. Why is that? Well, because f of naught equals, by that definition, minus f of naught, and that means that 2f of naught equals naught, and so f of naught is 0. Okay? It doesn't work if it's discontinuous, because you could have an even function like this. An odd function. We're talking about odd function. Here's an odd function, and that's discontinuous at 0. And so f of 0 is not equal to 0. Okay? 2, for any alpha element of real, integral from minus alpha to alpha, f of x dx equals 0. And again, intuitively, that makes sense, because if you've got an odd function, and then if you integrate it from 0 to alpha, say where alpha is positive, then you get some value, but then if you integrate it from minus alpha to 0, you're integrating the same values again, but the negative. So you'll get the same value of the previous integral, but with a negative sign. So proof of that would be integral minus alpha. I'll leave you to fill in the details here. Okay, leave you to fill in. We never write this like that. We always put the f in. Okay, and now here make x hat equal to minus x. So leave you to fill in all the details, right? Because what's going to happen here is that's going to go alpha to 0. We're going to have f of minus, which equals minus. The d by dx is going to give you another minus, so that's going to give you a plus. So we're going to have from alpha to 0. Switch it around, becomes minus from 0 to alpha. Okay? Leave you to do that. And then, in fact, I think this exercise is in the problem sheet. Integral from minus alpha to alpha g of x dx is equal to 2. Integral from 0 to alpha g of x dx. Leave you to prove that. Okay? Again, that this is even, so integral from 0 to alpha will be something if alpha's, and then integral from minus alpha to something will be integrating the same thing again, because it's even. Okay? And this one finally, leave as an exercise. F times g is odd. F times f1 is even. G times g1 is even. Leave you to prove those. Okay? And so now finally we get to Fourier series. for functions of period 2 pi. So let f be a function of period 2 pi. And the question is, can we write f of x in the form f of x equals a naught over 2 plus n goes from 1 to infinity a n cos n x plus b n sine n x. Okay? And the answer is, depending on certain conditions on f, yes, we can do that. Okay? Now, if you think about it, remember I was talking last time that if you have any vector in the vector space, you can write that in terms of the basis functions of the vector space. And so what we're saying here is that the cosines and sines, they're like a vector space. They're like basis functions in an infinite functional space. Okay? So two things to ask is, but what about this term? That's not a sine or a cosine. But it is, if I multiply that by cos naught x, cos naught x is 1, I get that. Second question to ask, how come that's a 2 here, but there's no 2 here? There's no 2 here, right? I don't know. That's just how they write it. Doesn't make any difference. If you wrote it somewhere different, you'd have a different definition of a naught, etc. But that's just the way you write it, okay? So if we could write it in this form, could we figure out what the a's and the b's are? So can we find a naught, a n, b n? Well, let's assume that we can integrate, well, f of x dx equals, let's assume that we can take the integral of the sum to be the sum of the integrals. So we'll get integral minus pi to pi a naught dx over 2 plus the sum, n goes from 1 to infinity, integral from minus pi to pi a n cos dx bn n pi x dx. Okay? So what does that give us? This one here gives us a naught over 2 times 2 pi. Okay? What does this give us? Well, cos nx is even, so this is 2 times the integral from 0 to pi cos nx. An integral from 0 to pi of cos nx is 0, so that's 0. What about this here? Sine nx is odd, so integral from minus pi to pi is 0. From up there, take alpha to be pi. Okay? So these all disappear. So you see how we're using these types of results here in order to save us doing work. Okay? So this is one thing I say to all students, that to be a really good mathematician, you have to be lazy. Okay? So you look at that and you sort of say, right, you could go straight in, integrate it, put the values in, get 0. Or you could step back for a minute and say, is there a trick I could use that gets the answer without having to do a lot of work? And the answer is yes, there is. So before you dive into something, sit back, look at the problem and see, is there a clever way I can do this that'll save me time? Okay. So now we've got a0 equals 1 over pi, integral from minus pi to pi, f of x dx. So that's brilliant. We've got an. Right? What about the bn's? How are we going to get those? And the an's? What about, so let's say am. We want to find am. So out of all these an's, we want to find the value when n is equal to m. Okay? So remember, go back to vectors. If you had a1i plus a2j equals b1i plus b2j, you know a1 is b1, a2 is b2, right? Strictly speaking, what you should do is you should take the dot product with I. If you take the dot product with I, then that's a1 I squared, which is 1. J dot I is 0. So you get a1 here, here you get b1. Here, take the dot product with j, a2, b2. So you got a1 equals b1, a2 equals b2. So when you say this is equal to this, and this is equal to this, that's what you're actually doing. So what's the equivalent of dot product, so to speak, in this one? Well, it's, if you think about I dot I is 1 comma naught dot 1 comma naught. So you're multiplying I by itself, and then you're taking the sum. What's the sum here? The sum is an integral. So we have to integrate something. Here we multiply by I and j, our basis functions in inverted commas. Here our basis functions are cos nx and sine nx. So what we do is we multiply by cos or by sine, and we integrate. And we hope that'll give us the right answer. We hope we'll be able to do something with that. Okay? So let's multiply by cos mx dx and integrate from minus pi to pi equals a0 over 2 integral from minus pi to pi cos mx dx plus the sum, n goes from 1 to infinity, an times integral from minus pi to pi cos nx cos mx dx plus bn integral from minus pi to pi sine nx cos mx dx. Okay? So all we've done is multiply by cos mx and then integrated from minus pi to pi. Now, if you look at this, What's that integral? Minus pi to pi of cos mx. That's 0. Okay? Cos mx is even, so it's the integral from 0 to pi cos mx, and that's 0. So the a0 disappears. Now, wouldn't it be brilliant if all these b's disappeared? And wouldn't it be even more brilliant if all of these disappeared except for the m? And then I'd have just am on this side, and then I'd got it. Okay? Well, so we know this one is 0. What is the integral from minus pi to pi of cos nx cos mx dx? Now you need to remember that is a half the integral from minus pi to pi cos n plus mx plus cos n minus mx. Okay? From the formula, trigonometric formulae. Now look, if m is not equal to n, this is even function. Integrate from 0 to pi is 0. Integrate from minus pi to pi is 2 times integrate from 0 to pi. That's 0. Likewise, this one is 0. So that's equal to 0 if n is not equal to m. Why do we take out the case n not equal to m? Well, if n is equal to m, this is 1. So if n is equal to m, this is equal to half the integral. That one's still 0, minus pi to pi dx, and that's equal to pi. So it means on the right-hand side of this infinite sum, every single term disappears except the am term. And so therefore we have integral from minus pi to pi f of x cos m pi x dx equals am pi, and that gets us am. How do we get bm? Leave as an exercise. Bm is integral from minus pi to pi f of x sine mx dx divided by 1 over pi. Okay? Because am here gives you 1 over pi. Okay? And so now you see why it is that we put the half in there. By putting the half in there, all of these are 1 over pi. Right? 1 over pi times an integral, 1 over pi times an integral, 1 over pi times an integral. And now you see the equivalent of saying I dot j is 0, so all these things disappear. The equivalent of that is saying integral from minus pi to pi cos nx cos mx dx is 0 if n is not equal to m, and it's pi, non-zero, if n is equal to m. That's the equivalent of doing a dot product. Okay? So what we say, and these are in the problem sheets. we define that to be pi times delta nm, where delta nm is the Kronecker delta. Make sure I spell this correctly. Remember what the Kronecker delta is. That's 0 if n is not equal to m, and it's 1 if n is equal to m. Okay? So the only difference now is, going back to here, if we multiply by dot product by I, that disappears, and very conveniently I dot I is 1. Here, the equivalent of I dot I gives you pi. So if you wanted to, you could say the orthonormal basis functions are take the causes and sines and divide by 1 over root pi. Because then when you do this equivalent of dot product, this is actually called inner product, you'd have 1 over root pi, the bottom line, and then that would give you delta nm. Okay. So if you think about it, it's pretty remarkable that something like vectors and something like calculus looked like two completely different fields, and you've been taught them as completely different fields, actually have very similar ideas in them. And that's one of the beauties of mathematics, I think, is that you look at very different areas of mathematics, you learn them separately, and then if you sit back and think about it, you see that actually similar ideas are happening in all these different fields. So you should now be in a position, you should be able to do all of sheet 1. You should also now be able to do actually sheet 2, question 1, and the first part of question 2. So what we will do the next time is we will talk a bit more about sine and cosine series, and then we'll actually state the Fourier definition theorem of the Fourier series, and then we will work out some more Fourier series. So we'll do that on Monday. Okay.